I tend to keep too many tabs open here. All right. So here were the kind of the steps, hints, I don't know, whatever you want to call it, as far as optimization problems. I've put this on my website as well as a PDF. Identify the quantity we're maximizing, minimizing, write and label an equation of that quantity, get it in terms of one variable. And then the calculus part, find the critical points. In other words, where, and again, it's easy to kind of not see the forest for the trees. You heard that expression before? To not be able to see the forest for the trees. In other words, you get so caught up in the details, right? You get so caught up in all the trees that you can't see the big picture. You know, the forest, okay? So that's easy to do here. You know, you're doing a problem and you're kind of, okay, do I do this and then I do this and then I got all this calculus to do, or I got to put in my calculator, what do I plug into? And you always got to step back a little bit and see the big picture of what's going on. Remember, the reason we get down to step 4, find the critical points of the equation, is we're trying to find, we've got a function and we're trying to find its max, its highest point or its lowest point, its minimum. Well, where can those happen? Well, they could be where, you know, in a flat spot where the derivative is 0. Could be at a sharp point, you know, where the derivative is undefined. That could be a max. Or it might be up at an endpoint, right? So those are the places we have to look for a max or a min value. So that's the whole point for steps 4 and 5, okay? Step 6 is really important. Every time we do a max or min kind of a problem, there has to be some sort of a justification of why that answer you give in step 7, why that answer is a max or a min. Like, as I was going and looking at your work on the business packet, those of you that did number 3, very easy little problem, number 3, in the business packet, probably took 30 seconds, really. But you have to have that step 6. You have to have some sort of justification there. There's only one candidate, but you have to have, you know, why is it a max or min? Now, I've given you some possibilities. A lot of times it would be a list of candidates. That's your justification of the max. If there's only one candidate, a little number line could be useful. But in some problems, there could be some other justification for why it's a max or min. That's where you got to be able to see the big picture to understand what would be a legitimate way of you know, just saying that, yes, this is a max or this is a min. You have to understand what's happening to be able to do that. So we'll talk about that as we look through those. Now, on my website here, on our class website, on School Fusion, not only the videos, but down here, under files, I've got the answers to the business packet kind of worked out. So you have access to that as a PDF, and that'll be part of our homework too, and so you can use that. Now, I use it appropriately. I mean, really what you want to do is you want to work out the problems, and you want to get them set up on your own. Don't go there and see how to set it up. Obviously, that's not going to help you for the quiz on Friday. And I've got those hints. Those hints I just had up there for optimization are here as well. And then, or not hints, I don't know, steps or whatever you want to call it. And then the new thing we're going to talk about today is I've got something on there for that as well. So you can use that. Matter of fact, let's just talk about the business packet while we're on it. I've got, this is what's on the website, this PDF file of me having worked out the business packet problems. Now understand that my point in doing that, of working them out, was to give you something so you can see how the equations were set up and so forth to help you along the way. I did not fully go through and do the justification parts of that. So you've got to hear me carefully on this, is when just because you go through on the homework and you see what I did on here and think, well, if I do it just like that on the quiz, that'll be just fine. Okay? I wasn't being graded on this. So I may have skipped a step or two or something in the justification aspect of it, okay? So you have to understand that's necessary. For example, on number 3 here, they give you this revenue equation. They want the maximum revenue. Well, geez, we're already to step 3. You've got the equation. It's in terms of one variable. You're ready for where are the possibilities? Well, where the derivative is 0. Now, why? A great justification on this one could be there were no endpoints, the derivative is never undefined. What kind of a graph is the revenue graph? Just look at it. It's an upside down parabola. Where's the max going to be? At the vertex, which is when the derivative is 0. So a little sentence right here, the revenue equation is an upside down parabola. The max has to be at the vertex where the derivative is 0. So this 200 has to be the max. Right? So step 6 on what I had up there earlier, you have to give some justification of why it's a max. In that case, it might be that. Now, you could also do a number line. You could say, well, since I only have one candidate, since they gave me no endpoints or anything like that, I could make an R prime number line. And I could put 200 on it. And take 100 and 300. And I could put 100 in here and it comes out positive. Put 300, it comes out negative. And then I could write a sentence that says, okay, since R prime is always positive before 200 and always negative after 200, remember we talked about always for global maximum, then R is always increasing before 200 and always decreasing after 200. Therefore, 200 is a max. So you just have to have something in there. And a lot of you did not have that in your business pack. You would have got some of the points, but not the whole thing. So make sure you do that. Okay, out from this room before?
Yes.
We go out, we take a right, but do not go north. We turn, go by the weight room, go across the parking lot into the practice field over there, okay?
I know.
Pass the weight room.
Sure we did.
Pass the weight room.
And I got your hoodie frame.
Oh, yeah.
Today.
You're not gonna let me leave it there again?
Does that make me a real plastic? I would protect you, Troy.
It was funny.
Not in mine.
Why are you walking on it?
All right, if we don't get time to work on homework, that's not my fault.
Oh,
Well, we'll try. We'll pick up the pace here a little bit.
No.
No thanks.
Whoever's watching the video. Well, I can't stop and start over. I could. So I'll do two videos. So. All right, we were in a fire drill. Fire drill. That's what happened. Sorry.
Please evacuate wherever you are.
I can hear the fire alarms going off in your house. You need to get out.
All right. So on number 8, onward here to number 8 in the business packet. If you had a negative 1,833 units or something like that, then you hopefully thought, well, something's not right.
If we buy back what we sold.
The question in number 8 asks for the minimum average cost per unit. That's the C-bar equation. C is the total cost of producing X units. So the average cost per unit is the C-bar equation. That's the cost divided by X, the number of units produced. So you have to take the equation they gave you, the cost equation, and divide it by X. Then I went ahead and simplified it algebraically just by dividing each term by X. But you wouldn't have to. Again, you've got your calculators, which you can let that do the derivative for you. So when we do C-bar prime, we get this equation, we set that equal to 0. Of course, there is a place where the derivative is undefined, which is at 0, but you're not going to make, if you make 0 units, there's no average cost per unit either, because you can't divide by 0. So that's not it'd be an endpoint, but it doesn't give you an amount, a minimum cost. It'd be more like an infinite cost, kind of thing, dividing by 0.
That's not good for business.
Yeah, no. Dividing by a very small number would give you a very large average cost. So the only real candidate you have is this 4.759. Now, to answer the question, you have to think about this a little bit. It says, find the number of units X that produces the minimum average cost per unit. Now, 4.759 would be where this C-bar equation is a minimum. In other words, it might, but it's not a parabola or anything, so we can't really do that. But it comes down and like so, and that's 4.759. So you might say, well, I should do a number line. Yes, you should do something like that. You put 4.759, and you put in a 4, put in a 5, you get a negative, you get a positive. So that's clearly a minimum. However, you've got to answer the question. How many units should you produce to get the minimum average cost? Is 4.759 an acceptable answer? What kind of thing can we make that we would make 4.759 of them? I can't think of very many things. I mean, it might be
kittens.
Yeah, kittens. I opened this up for that one. So if you are answering a real life problem, you have to make sure that the answer makes sense in the context of the problem. So what would you do then? What would you do next to really finish this out?
Round up to the nearest king.
Would it be? Well, it's probably what's going to happen is 4 would be back here somewhere, and 5 would be here somewhere, and you'd want whichever one of those was the minimum. So you would have to take 4 and plug it back into C-bar, and you would have to take 5 and plug it back in to the original and see which of those is the littlest. Okay? So again, in the business packet, I take it this far, the mathematics is setting it up, but in some of the cases I may not have went and then finished the answer in the context of that. Okay? And I'm not sure which one it is here. It's probably 5, is my guess. But, okay, so you would need to give an answer that would make sense. Now, in this case, I just said units, but if it was, we're going to do an example in a minute about radios, for example. So it would be obvious that, yes, we have to have a whole number of those that we can make. Okay, so make sure you consider that when you're looking at the problem. All right, let's go into the book problems. I just have a couple of quick comments to make about number 27, and then I want to talk about 21 just a little bit. Now in 27, again, we had this thing with the square base. So we had a thing that looked like this. We're going to use 100 centimeters of wire to create this thing. Now there were 2 problems you were supposed to do. Both answers in A and B in 27 came out the same. What was it? A cube, right? 25 thirds. It should have been, not only X was 25 thirds, but also Y is 25 thirds. It came out to be a cube. And the lesson from that is, unless something unusual has been added to it, like maybe the cost of the vertical wires here on the box was a different type of wire than the wire down here, then it may not come out to be a cube. But in this case, what we have is we have a fixed amount of material to make this shape. The largest volume we can make with that amount of material and the largest surface area both come up to be a cube. So it's not really surprising, but the mechanics of working through the problem is kind of what I wanted you to work on here. So for part A, you had to do volume. Well, that's the x squared y equation. For part B, it was its surface area. What's the surface area of that picture? What'd you have? 4xy plus 2x squared. Surface area is just the area of the surfaces. Well, you have a surface here that's x squared, and you have a surface here that's x squared, so that's 2x squared. And then you have this front surface, which would have an area of x times y, and you have 4 of those around. So it's not like you have to memorize surface area, you just have to know what surface area is. So these would be the 2 things you're trying to maximize or minimize, part A, part B. And what was your constraint? The 100 centimeters of wire, what did that look like? Uh-oh.
4H plus 8W is equal to 100. I used H and W.
So with X and Y, it would be what? 4Y plus 8X equals 100. Okay? Now, I promise for those people listening in the video that on the next one I'll actually write it so you can see it. But now you just have to hear it. So 4Y plus 8X is the pieces of Y. So we have 4 pieces that are Y, we have 8 pieces that are X. That has to add up to 100. So that gives us our equation to substitute in, and we go from there. Okay, so that was, I just want to make sure we were setting things up correctly there. So for number 21, okay. Number 21 was related to number 19. And number 19 talked about a projectile launched from the origin, which means it's going to be a parabolic path, okay? And the equation they give you in number 19, you can see, hopefully you can see, is a parabola. Now I've put it into my calculator here, and I mentioned this to you at the end of the period on Friday of how you could do this. But this is number 19. Y, think about a Y being there. The one they give you in number 19 is Y equals, and then M, G, and V are just constants. M is the slope, which is the launch angle. Okay, G is gravity, and V is the velocity that you launch the projectile. So X is the horizontal distance it travels, and Y is the vertical distance it travels. And so you can, if you look at it, you see an X here, you see an X squared here with a negative right here, so that's going to be an upside down parabola. So it makes sense that the picture would look something like this. Well, in 21A, it said, they gave you this equation for R. Now what was R in 21? What did that stand for? Range, meaning what? How far it traveled. Now I want you to think of the example of, in track and field, think of a shot put. Okay? Think of this projectile as a shot put, and we want to maximize the range. Obviously, that's the whole goal of the shot put, is to see how far we can throw it. That's what we're trying to do. So they wanted you to say in 21A, and I told you to skip 21A, but in 21A they were just saying show that equation for R comes from this equation, right? Well, okay, so really isn't it just solving that equation for X? What I did was I put a 0 in for Y, because what happens when Y is 0? The projectile is on the ground, right? So how far it travels horizontally is going to be determined by where it is when it's on the ground. So I put a 0 in for Y, I kept M, V, and G in there, and I just told the calculator to solve it for X. Now, it's not that hard to do by hand, and that's what they wanted you to do in 28. So I went ahead and let the calculator do it. When's it going to be on the ground? Well, clearly it's on the ground back here when X is 0. But also this. Now, if you look at that, that's the same as they give you in 21. The 2 and the V squared's on top, the G's on the bottom, and then you've got M on top, and you've got M squared plus 1. Now, in 21, they said, let's hold G and V constant. Of course, gravity is a constant, and V is going to be the velocity we launch it. So we're going to hold those constants, so they pull those out in front, and let our variable be M, the launch angle. So what the question in 21 is saying, what angle should you launch this projectile to get the maximum distance? Shot putter would be pretty interested in that. Now, if you go ask Mr. Larson what angle he teaches his shot putters, I don't know if we got any shot putters in here now. What angle would he say? Well, if you look at the answer that we get here, the answer came out to be what? M equals 1. Well, what's a slope of 1? 45 degrees. Now, I went ahead and I put that in. All we had to do is do the derivative of it. Here's what that would look like. The derivative with respect to M, it came out to be this. Now, it's not a hard derivative to do by hand. This would just be a constant, which would just hang out there. Then you would just do a quotient rule on this. Okay? And it comes up to look like this. Now, we now want to take that derivative, set it equal to 0. Well, this is pretty easy to set to 0, quite honestly. I mean, it's a fraction. When's a fraction 0? When the top is 0. Well, that'll be when V is 0. Well, that's the velocity. Well, if you don't throw it with any velocity, it ain't going to go anywhere. So we can ignore that. So when's M squared minus 1 equals 0? Plus or minus 1. So it doesn't surprise us when I tell it to solve and it gives me plus or minus 1 and then this other stuff, which I'll ignore. Of course, we're not going to throw it with a slope of -1. That's not going to go anywhere. And so the answer that we're interested in is a slope of 1 is the max. And then you can justify it, and you know, it's really the only candidate. You can do a number line, the whole thing. There's our max. Now, the interesting part of this that I want to expand on just a little bit is that if you ask Mr. Larson what angle he teaches his shot putters, and I've talked to him about this in the past, well, he would give me a couple answers. Number one, he doesn't focus on a whole lot. If somebody throws it at 45, he says about 45 degrees, that's probably good enough. But if you ask him to, but what really would be the ideal angle to throw it, he wouldn't tell you 45. He would tell you more like 42 or 43 degrees. Now look at our picture up here and compare that to a shot putter and tell me what's different. You don't throw the shot put from the ground, right? What we're saying is for a maximum distance here, you would want this angle to be 45. A shot putter actually throws it from about shoulder level or a little higher as they release it. So that might be, say, here. Well, what's the launch angle here compared to back here? A little less than 45. So would there be a perfect launch angle for every person? Or would there be one launch angle that would be best for every person? It would depend on what? how tall, their release point, how tall they are. A taller person would have what? Little lower angle that they would want to shoot for. Now, if you go back to this equation and you ask Mr. Larson what's the most important thing about throwing the shot put a long ways, he would say what? How strong you are, which is determined by the velocity, right? So there's two variables in here that would determine how far you throw it. The launch angle and your initial velocity. Well, the one that you would have the most control over would be your initial velocity, and so you get stronger and so forth, and okay, and you fix that. Now, if you got to an elite Olympic level, Olympic caliber shot putter, you know, who maybe has taken all the steroids they can possibly, I mean, they've gotten just strong as they can possibly get, right? And they're maybe not going to change their velocity, okay? So then they might do some, you know, some video analysis and really look at their launch angle and maybe try to adjust that, okay? And maybe half a degree would make a difference, okay? So anyway, that was the point. The hardest class of all the math classes and stuff I took in college, the hardest class I took was a 1 credit hour PE course. Now, it was under PE, but it was because it was for my coaching endorsement. It was called Biomechanics for Coaches. And it was basically kinesiology, which was essentially the physics behind the different sports mechanics, the different things you would have for coaching different sports. And so it was a lot of problems like this. So it was really a lot of math, a lot of physics. It was 1 credit hour. The guy who taught it was, well, he was crazy. But anyway, he was kind of famous. Ask Mr. Limbach sometime about Dr. Johnson from UNL. He was our anatomy and anatomy teacher. And I had to take anatomy. That was probably the second hardest class I took in college. Both of those for my coaching endorsement of all things, which you don't even have to coach. But anyway, so looking back, I might not have taken those classes. But of course, Mr. Limbach was in it for a different reason. But it was really hard. That was one of the class at UNL, one of the classes at UNL. You could not transfer anatomy credits from any other college. You had to take it with Dr. Johnson. He had something wrong with his eyesight, so he had to wear sunglasses inside. So he always had sunglasses on. So it was he was scary. He was just kind of mean and hard to. He was anyway. Just ask Mr. Limbach sometime about Dr. Johnson at UNL. So anyway, he was also the teacher for that biomechanics class. So it was hard. All right. So let's move on. Today's topic, if you would turn in your book to page 250. Now, for our quiz, as you're getting your notes out and turning to page 250, our quiz is over 3 sections in chapter 4. Section 4.4 was parametrics. 2 equations, an x equation, a y equation, both in terms of t that describe motion. We talked about horizontal velocity, vertical velocity, you got speed, slope of the path, you had some things you had to know. Section 3 that we just got done talking about last couple days is optimization. So you're going to have some of these story problems with maximum. Now we're going to do some more. Today's homework is going to be some more optimization. There's going to be a mixture of these things as we go through the week. Because that's one of the hardest things to do is to just, okay, what kind of problem am I dealing with here? Is this a parametric? Is it an optimization? What is it? What is it that I need to be able to do here? And that's where I want this not to be really a lot of memorization of the different steps, but to be able to see the forest for the trees, to be able to see the big picture, be able to read a problem, and just have the understanding of what needs to be done to do this problem. All right, so section 4.5 is called Related Rates. Related rates. Now, it seems that these problems seem a little bit like the parametric in the sense that they have they deal with motion. Okay, most of the time. The term related rates, very simply, the problems are going to deal with rates of change, which are derivatives, of course, and within the problem, there are going to be various rates, various quantities that are changing that are related to one another. As one changes, it causes the other to change. Okay, a simple example would be, let's take two cars starting at at the same spot. One travels north, the other one travels west. Well, there's several distances there that are changing as the cars travel. There's the westward distance of the car going west. There's the northward distance of the car going north. And there's the distance between the two cars on a direct line, on a diagonal, is changing as well. Okay, so there'd be three different rates right there that would be changing. And I've got some pictures here. Now, hopefully these help you to visualize some of these situations. But, of course, when you guys work your problems, you won't have these pictures. You'll have to kind of draw them and visualize them yourself. Okay, here's an example. A 60-foot rope is looped through a pulley 36 feet above point G on the ground. A lantern is attached to the end of the rope. A 6-foot man holds the rope's other end at the top of his head, I guess to make it easy so it's the 6 foot tall, and walks away from point G at 5 feet per second. What is the rate of change of the distance between the pulley and the man's head? That would be a typical related rate problem right there. Or we might ask, what's the rate of change of the man's shadow length when he is 40 feet away from point G? Or when is the tip of the shadow P closest to G? Or so forth and so on. So if I go ahead and let the man walk here, okay, he's moving right along. But again, related rates. We have several quantities in this problem that are changing. This distance is changing. This distance is changing. This length right here is changing. The length of his shadow is changing with respect to t, with respect to time. And they're changing all probably at different rates. And at different times they have different rates. Now, there's one rate for sure here that's a constant. What is that? How fast he walks. 5 feet per second. Now what, with the labels that are up here on the picture, and that's one of the most important things in this problem, is proper labeling of the different quantities. What would we call the rate he's walking 5 feet per second using the labels in the picture? That's a rate, so it would be a derivative. What rate of change would that be? That'd be the rate of change of x. So what would we label that? X prime, or dx over dt. The rate that he is walking is the rate that x is changing. As he walks, x is lengthening 5 feet every second. That's what 5 feet per second means. So we would call this number here, the 5, x prime. Okay? Again, as you'll see, one of the important things we do right off the bat in these problems is we identify and label the various numbers that were given in the problem. And again, these problems are very easy to recognize because they have all kinds of rates in them. Feet per second, miles per hour. I mean, right away you hear these rates and you think of this type of problem. Okay, here's another one. We've got a pool that's draining. Okay? And it says here that it's draining at a rate of 12 cubic meters per hour. Now, just looking at those units, 12 cubic meters per hour, what label would you put on that? What's cubic meters? Volume. So cubic meters per hour would be V prime, dV dt. And notice they've stuck a negative on there. Why? Because the volume is decreasing. So if V is decreasing, the volume of the pool. So if V is decreasing, think of the chart, V decreasing, V prime is negative. So even though in the problem it wasn't negative, when we write it down to use in the problem, we will write a negative. Okay. So also what do you notice is happening? You also have H is changing here, the height of the water, the depth of the water. That's changing. That would be H prime. That's what they want us to find. They say, what's the rate of change of the depth at the deep end when the water is 2.5 meters deep? So right about here. How fast is the height decreasing? That's a rate that we'd want to find. Okay? Now, it goes faster and faster, doesn't it, as it gets down here because of the slanted part. When it was up here, it was dropping at a constant rate. Right? But once it gets down into here, it starts dropping faster and faster and faster. So that rate is changing. Okay? And so we're going to find it at a certain instant, like when the water is 2.5 meters deep. That'd be when H is 2.5. We'll find H prime. Okay? Here's a baseball example. A runner runs down the first base line at 20 feet per second. How fast is his distance from second base changing when he's 10 feet from home plate, or 45 feet, or 100 feet? Okay? So here he goes. Now, we didn't label this, but if this was X right here, then X prime would be the 20 feet per second. Right? That's how fast he's running right down. 20 feet per second. So that would be the rate of change of this length right here. How fast is his distance from second base? So we'd have this distance. Here's how far he is from second base right here. Now you might say, well, wait a minute, he's got to go around here. No, if it says how fast is his distance from second base, we mean his direct distance from here to there. That would be changing. Now I've got a little better picture of that. Let's do this one. Runner starts at home plate, runs around the bases at 20 feet per second. How fast is his distance from, now this time we're saying from home plate, changing. So C is going to be his distance from home plate. Now right now, what is C prime? 20 feet per second, because that's how fast he's running. Okay, but now he rounds first, he's headed to second. Now how fast, is C prime still 20? No. Right here is 20. Whatever we want to call that distance, maybe we call that A. Now A prime would be 20, but C prime would be something different. Now, would it be positive or negative? C is still increasing, right? So it'd be a positive, but is it faster or slower than 20? Slower than 20, isn't it? Okay, now what happens when we round second? Now it's negative. C prime would be negative. C is now getting less. Okay? And what would C be right? What would C prime be right here? Negative 20. Because now he's running straight towards home at 20 feet per second, so C would be decreasing at a rate of 20 feet per second. Okay? Now, again, we're going to get into how we do these calculations and so forth here in a minute. Matter of fact, we're going to start with, whoops, not that one. We're going to start with this one. All right. So what we have is a 6-meter ladder against the wall. The bottom is pulled or pushed at a constant 1/2 meter per second. We're going to pull it out. We're going to pull the bottom out at 1 meter per second, 1/2 meter per second. How fast is the ladder top sliding when it reaches 5 meters up the wall? Now, I would never ask you a problem where I ask for 3 different answers in one. We just say 5 meters. Let's just say when it's 5 meters, which is what I show right here. Okay, so if we're going to slide the ladder, we're going to slide it out like that. Now, what do you notice? It says the ladder, we're going to pull the bottom out at 1/2 meter per second. Now, if you watch carefully, that down there, X should be coming out at a constant. Okay? Now, watch Y. What do you notice about Y? It starts slow and it speeds up at the end. But X is changing at a constant. That's what they tell us right here. Okay, so let's try working this one. So, you're not given the picture on this one. You're just given that description. Okay, a ladder's leaning against a wall, 6-meter ladder. So you would draw yourself a picture of a wall. We would put the ladder in there. Now, I think it's helpful to put some arrows that show the direction of travel if you've got something that's moving. Okay? I'm going to go ahead and label these much like they did. Now, I don't have to use X and Y. I could use A and B or use whatever you want here. Now, the question, and some people would put Z for the hypotenuse, I would go ahead and put 6 here. That's because as the ladder slides down the wall, x is a changing quantity. Y is a changing quantity. But what about the hypotenuse? Constant. So any numbers that are going to stay constant in the problem as the motion is happening, go ahead and label those as constants. If they're changing, they need a variable. Okay, now the next step, and if you look on page 251, it says, third of the way down the page, in italics, they give it, and we're going to write these steps down later. But it says, this is basically your strategy. Write an equation that relates two or more amounts that vary with time t. Differentiate both sides with respect to time using the chain rule, meaning implicit differentiation. The resulting equation relates the rates at which those quantities vary. Solve this equation for the desired rate. So let's think back to the problem. The problem said the ladder, 6-meter ladder, was sliding down the wall. They wanted us to find how fast the top of the ladder was sliding down the wall when the top of the ladder was 5 meters off the ground. So let's write down what they just told me. First of all, we want to find what is it they want me to find? The rate that the ladder was sliding down the wall. What would I label that? Y prime. Now, I probably should make you label these dy dt, but I'm not going to. I'll mix it in sometimes, but I a lot of times like to just use y prime. But we have to remember that that's with respect to t. Okay? And that is what we're trying to find in this problem. So when I write out the steps of how we should do these, the first thing I'm going to say is identify the quantities in the problem that you're trying to find and that you're given. So that's what we're trying to find. What else are you given in the problem? I know we can't see the problem anymore. Let me put it back up. That would help. We know the ladder is 6 meters, but that's not a big deal because I've already got that in my picture. Oops. What else am I given? The half meter per second. What would that be? That's x prime. That's x prime. Or dx dt. Is it positive or negative 1/2? X is increasing. So x prime has got to be positive. Okay? What else am I given? We want y to be 5. We want to find the rate. We want to find y prime when y is 5, when the ladder is 5 meters off the ground. Now, some people say, well, why don't you go ahead and put a 5 in here for y? You don't want to do that because that in the picture, y is changing. Okay, this is a number we're only going to use at the very end. All right, and that's one of the hardest things about these problems is people want to substitute stuff in too early. Okay, so there's a difference between things that are constant in the problem and not changing, and those that are changing. Okay, very important. All right. So, in the italics on page 251, it says, write an equation that relates the various quantities in the problem. So, we have the various quantities in the problem are x and y. What's a very simple equation that relates them? X squared plus y squared equals 36. Sometimes it's going to be very obvious what the equation is that you're going to have to relate them. Okay? Most of the time it's going to be pretty obvious. And a right triangle is pretty common. There's a lot of these problems, as you'll see in the ones I gave you. Well, think about the lantern with the guy walking, his shadow. And, that made, the distance from the top of his head to the pulling. There's all kinds of right triangles. One of the Pythagorean theorem is a pretty common one to use. Okay, now, here's where there's a lot of reasons these are different than optimization problems. Number one, these don't have anything to do with max and min. Okay, and they're all about rates. But the second thing where this is different is we do not have to get this in terms of one variable. We can have 2, 3, 4 variables in the problem. It doesn't matter. As long as we have enough information to plug into those, no problem. So the next step, if you look on the italics, it says write an equation that relates the varying quantities, then differentiate both sides of that equation with respect to time, with respect to t. So what would be the derivative of x squared? X prime. Now again, just to get us started, I'm going to write dx dt. That's implicit differentiation. Now, when we were doing implicit differentiation before, we didn't tack on an x prime. Well, that's because we were doing it with respect to x. And x prime in those cases would have been dx dx, which is just 1. So there was no sense to do it. Okay? But we're doing it with respect to t. So this is dx dt, or x prime. We have to tack on. Okay? Everything in here, all the derivatives we do in related rate problems are with respect to time. Plus what?
2y.
Times dy dt. Or y prime. If you want to use y prime, that's fine. Equals 0. Okay. On page 251, it says the last thing to do then is solve for the resulting rate. Solve for the rate you're wanting to. Now, I've already written this out, and it's dy dt that I'm trying to find. So what we need to do is just substitute in our missing values, and we're going to solve for dy dt. Okay? So, let's work backwards. What can we solve in here for y? Or substitute. Substitute in a 5. What do we substitute in for dx dt? 1/2. What are we going to put for x?
Y is 5, so
When y is 5, we'll know what x is. When the ladder is 5 meters up the wall, it will be a certain distance away from the wall. So we can just come to this equation and we can go x squared plus 25 equals 36. X squared equals 11. X, of course, could be negative, so x will be square root of 11. So get your calculators handy. There we go. We've got everything we need to find dy dt, or y prime. So we'd have 10 y prime. Go ahead and write some of this out. This, the 1/2 would cancel the 2, so this would be negative root 11. So y prime would equal negative root 11 over 10. Now, if you wanted to leave it in those terms, you could also just do a solve on your calculator. You could have just typed this in, and just call this variable a or something here and solve for it. Let it do that work for you. That would have been fine. Once you get to this point, if you let the calculator solve that, I'm okay with that. If you want to give a decimal, make sure you do 3 decimal places. Let's do a decimal on that just for the heck of it. What do we get?
Negative 0.332.
332, and units, very important. You have right units on your answer. This would be meters per, I think it was meters per second that they were using in the problem. It was meters and seconds. This is a rate. Now, does it make sense that was negative? Y is decreasing, so therefore y prime had better be negative. So there you go. At that instant, that's how fast it was traveling down the wall. That's a related rate problem. Very basic, kind of garden variety related rate problem. Okay? Now, let's do one that adds one little bit of complexity to it. This one right here. Okay? We got water flowing into a tank. A cone-shaped tank. Which would be kind of hard to balance, but we can imagine there's some supports. There are like grain tanks and there are some cone-shaped tanks. Another problem we do that's very closely related to this would be a cone the other way, if you ever drive by an elevator, a grain elevator, right, with the corn piled up on the ground, it makes a cone-shaped pile, right? And as they dump the grain onto it, the pile grows. And we talk about how fast is a pile growing as the corn is dumped at a certain rate. Okay? So these would be very similar problems. All right. So let's go to h equals 5. Let's do this one. So here's the problem. It says water is flowing into a cone at 2 cubic centimeters per minute. How fast is the water level rising when it is 5 centimeters deep? So if you had this problem, you didn't have the picture, of course you would start by drawing a cone. Okay? And hopefully we would know, I would help you that this is a cone with the vertex down. Okay, so I would, to make sure you get it drawn in the right direction. Okay? Now it says that the cone is 16 meters tall, or centimeters. So we're at 16 centimeters, and this cone has a radius of 4 centimeters. Okay? Matter of fact, maybe it would just be better. Right in here. Okay. So 16 here, 4 here. I said that the first step was going to be identify those things that were given to you in the problem and those things you're trying to find. Okay, what about the 2 right here? What would I call 2 cubic centimeters per minute? Look at the units. Cubic centimeters. That's volume. That's volume. 2 cubic centimeters per minute is volume per minute. It's a rate, so it's V prime. You've got to identify, again, you see miles per hour, meters per second, those are derivatives. Those are rates. So in our problems are going to be derivatives. So V prime is 2. How fast is the water level rising? Okay, what are they asking us to find then? In our units here would be H prime. So they're asking me to find H prime. And we want to find H prime when the water is 5, let's ignore these other ones, 5 centimeters deep. What would that be? That'd be H. So when H is 5. So those are the things we're given, and those are the things we need to find. So, in the book, it says, write an equation that relates those quantities. Well, volume, we're going to need a volume of a cone, right? That would be the equation we want. Anybody know the volume of a cone? Anybody know the volume of a cylinder? Yeah, they are in the front of the book. If you got a book that doesn't have a new cover on it. Now, I will give this to you. You'll do enough cones that you'll probably have it memorized by then anyway. But a cylinder is pi r squared h. A cone is 1/3 pi r squared h. Pi, yes, thank you. Pi r squared h. Okay? That's the volume of a cone. That is the equation we want. Now, here's where the additional level of complexity comes in this problem. Our next step, once we wrote our equation, was to do what? Derivative with respect to time. Okay? Now, what happened was when we did that, we got an x prime and we got a y prime, which was fine. It was okay to get multiple derivatives in there because we had an x prime that I could plug in, and y prime is what we wanted. Well, when I do this derivative, I'm going to get a v prime, but I'm also going to get r prime and h prime. Because look, as water fills up this tank, r is changing and so is h. Now that's bad because none of my information, nowhere here do I have r. Now you might say, well, nowhere here did you have x, but you did know y is 5, so you're able to find it. That's true. So we could do some things with that later, but it would be better to deal with it right now. the other complexity that would come in here is when you do this derivative, you'd have to do a product rule right here. Remember on the gateway test when we had those problems that had x squared y in them? And you'd have to do a product rule with that? Okay? So that makes that derivative a little tougher to do. All right. So when you get to this step, where you need to do the derivative with respect to t, you want to think ahead a little bit and say, okay, when I do that derivative, I'll have an x prime, I'll have a y prime. Do I have enough information? Yeah, I got enough information, not a problem. If I had 4 variables here and I had a whole bunch of information to plug in, that'd be great. I could just do the derivative. But in this case, I would look at it and say, you know what, I don't have r anywhere. I'd like to get r out of there. Well, how can I get r out of there? Could I get r in terms of h? If I could, and it's no different than that Shanghai problem where we had 1/2 b times h, and we said if we could get b and h related somehow, we could sub them out. That's the same thing. So look at this picture. Is there some way I could relate r and h? Why?
Because the radius, if you have the whole cone, it's 4 and 16, so it's going to always be.
Where? I don't see it. Yes, it comes from, you're right. Good job, Brian. Way to pay attention. Here's why that is. Because in this cone, it's similar triangles is what it is. Look at this big triangle. And look at this smaller triangle here. Those are similar triangles. Their sides are in proportion. And so what you could say about that is r over h is equal to 4 over 16. As the water fills up, r and h are going to stay in proportion to each other. So if I cross multiply those, I get 16r equals 4h. And like we said, we'd rather have h in the problem, not r. So we'd like to get r out of there. So solving for r would be a smart move. So r would equal 1/4 h. So the problems that are a little more difficult are the ones where you have maybe too many variables that you have information to plug in. Try to relate a couple of them somehow. Similar triangles is one way we often do it. Okay, somehow there'll be some information where you can do that. Now we can substitute. So we end up with this. So in place of r, I put 1/4 h. Now, I often see people do this part correctly, but then they try to now go do the derivative. Well, you don't want to do the derivative now because you still have a product here, and it's still, what should you do here? Let's multiply it together and simplify it, yes. So if we square 1/4, that's 1/16. Times the 1/3, that'd be 1/48. Pi, then we'd have h squared times h, which is h cubed. So you definitely want to take that and simplify it down to here. Now one thing that the calculator doesn't do very well is implicit differentiation. And now I think we might have found a place there where it would do that. And you can play around with that if you can, but I'm not sure how helpful that is. And the ones we're going to be doing, the implicit differentiation is not that hard. But if you find it, we'll share it with everybody, and that'll be okay. So the next step is to now go ahead and do the derivative with respect to t. So v prime or dv dt. The 1/48 pi is just a constant. It'll just hang out there. We'll bring the 3 down in front. 3, that'd be 1/16 pi h squared h prime. Right? We got to tack on h prime. We're doing the derivative with respect to t. We're not doing the derivative with respect to h. That's different than the optimization problems. In the optimization problems, if we had the volume, we were trying to maximize volume, and we had volume in terms of w, the width maybe, we would be doing dv dw. We'd be doing the derivative of v with respect to w. Okay? And so we weren't, in the optimization problems, we weren't tacking on x primes and y primes, and we wouldn't have been. Okay? This is something different. We're doing the derivative with respect to t. Okay, now we've got all the stuff we need to plug in. We can put a 2 here. For h, we can put our 5. And then h prime is what we're trying to find. Now, you can just type that right into your calculator and tell it to solve if you want. Or you can do some of it by hand. You can multiply the 16 over there and get 32. You can divide by the pi. And that would be 25 H prime. And you can divide by the 25, so you get 32 over 25 pi. That'd be positive. Would we expect this to be positive? H is increasing as the tank fills up. H is increasing, so we'd expect H prime to be positive. And this would be centimeters per minute, I believe, right? H should be centimeters because it's a height. And if you want to get the decimal equivalent of that, that would be fine. Okay? So I'll leave those up here. That is what a related rate problem looks like. Now, you decide what you want to work on first while you've got each other, and I'm here to help. But here's what the homework's going to be. Now I'm going to change it off of the assignment sheet a little bit. Okay? On the assignment sheet, if you look at where it says 4.5, we're only going to do number 4 and number 7 for now. Now that's the related rate problems. So if you'd like to try those, try your hand at those and see how you do, that'd be a good place to start. Okay, then we're going to finish the business packet. Now when I say finish, I mean the ones that are circled. We already did 3 and 8, so that leaves you 10, 12, 13, 15, 19, and 20. Now those are optimization problems. Okay, the max-min kind of problems. All right. Now in the other class, I kind of gave them some work time on number 19 in this packet. And then we talked about it a little bit. But we really didn't have much time for any other homework. So I thought this block, I'll just let you start where you want and I'll just help you. Okay? So that gives you about 20 minutes here. So you can start with the related rates if you want. Or you can go into the optimization. All right, rest of the time's yours to work.